September 1941, Ottawa, Ontario, the National Research Council Laboratories on Sussex Drive, 08:20 hours. The telegram sat on the desk of Geoffrey de Havilland Jr., Chief Aeronautical Engineer for the Canadian Division, its words typed in the clipped urgency of wartime communication: aluminum reserves critical. Production bottleneck anticipated 6 months. Explore alternative materials, immediate priority. The paper trembled slightly in his hands, not from weakness, but from the weight of what it implied. Without aluminum, there would be no fighters. Without fighters, the skies over Britain would belong to the Luftwaffe. Outside the laboratory windows, Ottawa moved through the routines of a nation transforming itself into an arsenal. Streetcars rattled past government buildings where clerks processed enlistment papers and ration cards. But inside this converted mansion on the edge of the city, a different kind of war was being fought, one waged with slide rules and wind tunnels, with mathematical equations scrawled across blackboards in the desperate hope that intelligence could substitute for material. De Havilland crossed to the window, watching his breath fog the glass. He was 30 years old, son of the legendary British aircraft designer, carrying a surname that meant something in aviation circles, but also carrying the burden of expectation that came with it. He had come to Canada 2 years earlier to establish a production facility for training aircraft, modest machines meant for student pilots learning to fly over the prairies. Now the war demanded something else entirely, something no one had successfully built before. The concept had been forming in his mind for months, ever since he had visited a furniture factory in Stratford, Ontario, observing craftsmen laminate thin sheets of birch into curved chair backs. The wood, when properly treated and layered, possessed remarkable properties: strength without weight, flexibility without fragility, and most intriguing of all, it was abundant. Canada's forests stretched across a landscape larger than all of Western Europe, filled with spruce and birch that grew straight and true in the northern climate. But wood was not metal. Wood absorbed moisture, warped with temperature changes, splintered under stress. Every engineering principle he had learned at university argued against using it for high-speed aircraft subjected to enormous aerodynamic forces. And yet, the telegram offered no alternatives. Aluminum was running out. Steel was needed for ships and tanks. Magnesium production could not be scaled quickly enough. Wood was not the preferred solution. It was the only solution. He turned back to his desk, pulling out sheets of calculations he had been working on quietly, almost secretly, knowing how his colleagues would react. The skepticism would be immediate and probably justified, but buried in those numbers was something remarkable. Certain species of wood, when laminated in specific orientations with adhesives developed for marine applications, could match the structural properties of aluminum alloys while weighing considerably less. The British had experimented with wooden components in the Mosquito bomber program, but that aircraft used wood for its fuselage while retaining metal wings and control surfaces. What de Havilland was contemplating went further: an entirely wooden fighter. Frame, wings, skin, everything. The door opened without ceremony. Harold Bishop entered, the laboratory's senior materials scientist, carrying a wooden sample that looked like it had been subjected to considerable violence. Bishop was 53, trained in chemistry at McGill, and possessed the kind of methodical pessimism that made him invaluable for identifying problems before they became disasters. Bishop placed the sample on the desk. It was a section of laminated birch, approximately 30 centimeters long, that had been bent until it fractured. The failure point showed clean, straight grain, no delamination between the layers. He tapped it with one finger. "They are getting better. This one held to 11,000 pounds per square inch before failing. The Sitka spruce samples from British Columbia are showing even higher resilience. But Harold, we are still talking about wood. Wood catches fire. Wood rots. Wood is what we used to build aircraft 20 years ago, and we stopped for good reasons." De Havilland picked up the sample, feeling its weight, examining the fracture pattern. "Every material fails, Harold. Aluminum fatigues. Steel corrodes. The question is not whether wood is perfect. The question is whether we can make it work well enough and quickly enough to matter." Bishop removed his glasses, cleaning them with a handkerchief. A gesture de Havilland had learned meant he was about to deliver an uncomfortable truth. "Geoffrey, I have run every test I can think of. Temperature cycling, humidity exposure, vibration stress, impact resistance. The laminated wood performs adequately under most conditions, adequately. But adequate means predictable failure rates. It means maintenance requirements we cannot yet quantify. It means asking pilots to fly into combat in an aircraft made from the same material as their grandmother's dining table. The comparison stung because it was accurate. Public perception would be brutal. The press would mock it. Allied command would question Canadian engineering competence. And if the aircraft failed, if it came apart in flight or burned too easily or could not withstand combat damage, the responsibility would fall on everyone in this laboratory. Careers would end. Reputations would be destroyed. Men would die. But de Havilland had spent the previous evening reading casualty reports from Fighter Command. Spitfires and Hurricanes shot down over the channel, their aluminum fuselages torn apart by cannon fire, their pilots lost to the sea. The Germans were producing fighters faster than Britain could replace losses. Canada's industrial capacity was growing, but the aluminum shortage was real and worsening. Adequate wood today might save more lives than perfect aluminum 6 months from now. He set down the sample and pulled out a folder containing preliminary design sketches. I want to show you something. This is not a traditional fighter layout. We cannot simply replace metal with wood in existing designs. The material properties are too different, but if we design from the beginning for wood, if we use its strengths rather than fighting its limitations, we might achieve something unexpected. The sketches showed an aircraft unlike anything in current production. The fuselage was a monocoque shell, a single curved structure without internal framework, relying on the laminated skin itself for strength. The wings were thick, almost stubby, using the natural rigidity of laminated spruce to eliminate the need for complex internal spars. The control surfaces were fabric-covered wood, traditional techniques applied to modern aerodynamics. It looked crude in the drawings, almost primitive, but the mathematics underneath were sophisticated. Bishop studied the designs in silence, his expression unreadable. The monocoque construction is clever. It distributes stress across the entire structure rather than concentrating it at joints and rivets, and the thick wing section might actually provide better lift characteristics at high angles of attack. But Jeffrey, this would require manufacturing techniques we have barely explored. The adhesives alone present enormous challenges. Casein glue, even the best marine grades, requires precise temperature and humidity control during curing. We would need factory conditions that simply do not exist outside specialized facilities. Then we build those facilities. We train workers who understand wood the way machinists understand metal. We develop quality control processes specific to laminated construction. De Havilland heard the intensity in his own voice and forced himself to slow down, to sound more reasonable than he felt. Harold, I am not suggesting this will be easy. I am suggesting it might be necessary. Bishop returned the sketches to the folder, carefully, as if handling something dangerous. You realize what you are proposing. Not just a wooden aircraft, but an entire wooden aircraft industry created from nothing in a country with no tradition of this kind of work. The British have de Havilland facilities with experienced craftsmen. We have lumber mills and furniture factories. The gap between those capabilities is enormous. I know. But we also have something the British do not have. Time. They are under bombardment. Their factories operating under blackout conditions, their workforce exhausted. Canada is 3,000 miles from the nearest German bomber. We can build without interruption, without air raids, without the constant fear that tonight might bring fire from the sky. And we have forests, endless forests, spruce and birch growing across provinces larger than most European countries. The raw materials are here. The question is whether we have the will to use them. A knock at the door interrupted the conversation. A young assistant entered, barely 20 years old, wearing the uniform of the Royal Canadian Air Force with the brevity of someone recently enlisted. Sir, Air Marshal Edwards has arrived. He is waiting in the conference room. De Havilland felt his stomach tighten. Edwards commanded the RCAF's procurement division, a practical man with combat experience from the previous war and little patience for untested theories. The meeting had been scheduled for weeks, but suddenly it felt premature. The designs were incomplete, the materials testing was ongoing, the manufacturing processes were hypothetical, and yet the telegram on his desk made delay impossible. He gathered the folder, the wooden sample, and a rolled set of engineering drawings. Bishop touched his arm as he moved toward the door. "Jeffrey, before you go in there, you should know something." "I spoke with colleagues at the University of Toronto yesterday. They have been conducting radar testing on various materials for the Navy. Wood, properly treated and laminated, shows significantly lower radar reflectivity than metal. It is not invisible, but it is much harder to detect at range. I did not mention it earlier because the implications seemed too speculative, but if you are about to stake your reputation on wooden aircraft, you should know that stealth might be an unintended advantage." De Havilland stopped processing this information. The Germans were deploying radar-directed anti-aircraft batteries across occupied Europe. Freya stations along the French coast tracked incoming bomber formations from hundreds of kilometers away. Würzburg systems guided night fighters toward their targets with deadly precision. An aircraft that could reduce its radar signature, even slightly, would have a survivability advantage that no amount of armor or speed could provide. "How much lower is the reflectivity?" Bishop shrugged, a gesture that contained both uncertainty and possibility. "The preliminary data suggests 50 to 70% reduction compared to equivalent aluminum structures, but the testing was limited and radar technology is evolving rapidly. I cannot promise the advantage would persist or prove tactically significant. Still, it is worth mentioning." It was more than worth mentioning. It transformed the proposal from a desperate improvisation into something with genuine strategic value. A wooden fighter would not just be a substitute for metal aircraft, it would be a different kind of weapon, exploiting an unexpected vulnerability in German defensive systems. De Havilland walked down the corridor toward the conference room, his footsteps echoing against hardwood floors installed decades earlier when this building served some peaceful civilian purpose. Through windows he could see the Ottawa River, gray and cold under September clouds, moving steadily toward the Saint. Lawrence and ultimately the Atlantic, where Canadian corvettes escorted convoys through submarine-infested waters. The entire nation was improvising, finding ways to fight a war for which it had been unprepared. Perhaps a wooden fighter was not such a strange idea after all. Air Marshal Edwards sat at the head of the conference table, reviewing documents with the concentrated attention of someone accustomed to making decisions that affected lives. He was 61 years old, silver-haired, with the weathered face of a man who had flown open-cockpit biplanes through European winters. He looked up as de Havilland entered, his expression neutral but his eyes sharp with assessment. "Mr. de Havilland, I understand you have a proposal regarding alternative materials for fighter production. I hope you are not about to waste my time with impractical theories." De Havilland set his materials on the table, carefully arranging them so the wooden sample was visible, so the sketches could be unrolled, so the mathematics could be explained. He met Edward's gaze directly, knowing that this moment would determine everything that followed. The truth was, he did not know if wooden fighters could be built successfully. He did not know if they would perform adequately in combat. He did not know if Canadian industry could master the required techniques quickly enough to matter, but he knew that aluminum was running out, that men were dying in metal aircraft that radar spotted from 100 kilometers away, and that sometimes the only way forward was through the impossible. "Sir, I am about to propose something that will sound insane. I ask only that you listen to the mathematics before making your judgment." He unrolled the drawings, revealing the strange, thick-winged fighter that existed only on paper and in calculations. Edwards leaned forward, studying the design with the intensity of someone who recognized that wars were won not just by courage, but by the willingness to imagine solutions that did not yet exist. Outside, Ottawa continued its transformation. Inside this room, a different kind of battle had begun. Fought with words and numbers and the audacious belief that trees might win a war, that metal was losing. October 1941, Downsview, Ontario. De Havilland aircraft of Canada factory floor, 14 and 45 hours. The smell of aircraft glue hung thick in the converted warehouse, a chemical sweetness that caught in the throat and lingered in clothing for hours after leaving. 300 workers moved through the space with the choreographed efficiency of people learning new rhythms, adapting skills honed in furniture factories and boat yards to the demanding precision of aircraft construction. The noise was different from a traditional aircraft plant. No riveting hammers, no metal shears, no welding torches. Instead, the softer sounds of wood saws, The whisper of sandpaper against curved surfaces, the careful tap of mallets settling components into jigs designed with tolerances measured in thousandths of an inch. De Havilland stood on the catwalk above the factory floor, watching the first fuselage take shape. It looked wrong. Every instinct trained in conventional aircraft design recoiled at the sight of laminated wood where aluminum should be, of glue joints where rivets belonged, of construction techniques borrowed from yacht building and applied to something meant to fly at 400 miles per hour, and yet the mathematics insisted it would work. The stress calculations held. The wind tunnel tests showed promising aerodynamics. Theory and reality were about to collide, and no amount of confidence could eliminate the fear that theory might lose. Beside him, Robert McIntyre wiped sawdust from his glasses, a gesture he repeated dozens of times each day. McIntyre was 47, a master carpenter from Victoria who had built racing sailboats before the war, and who now led the team translating engineering drawings into physical structures. He had thick hands scarred by decades of work with sharp tools and an intuitive understanding of how wood behaved under stress that no university education could replicate. McIntyre pointed to the forward fuselage section where workers were fitting interior bulkheads. The Sitka spruce from British Columbia is performing exactly as your calculations predicted. No warping, no splitting, excellent adhesion between laminations. But Mr. de Havilland, we are encountering problems with the casein glue in the wing sections. The thicker assemblies are not curing uniformly. The center remains tacky while the surfaces harden, creating internal stress points that could lead to delamination under flight loads. De Havilland had feared this. Casein adhesive derived from milk protein was the strongest natural glue available, used successfully in marine applications where moisture resistance was critical. But aircraft wings were not boat hulls. They flexed constantly under aerodynamic loads, experienced temperature extremes from ground level to high altitude, and could not tolerate any weakness in their structure. A delamination failure at 5,000 meters would be catastrophic and unsurvivable. What if we reduce the thickness of each lamination? Thinner layers would allow more uniform curing, though it would increase the number of gluing operations required. McIntyre considered this, running mental calculations about production schedules and worker fatigue. Possible, but it would add at least 40 hours to the wing construction timeline. We are already behind the projections you gave Air Marshal Edwards. Any further delays will give the skeptics more ammunition. The skeptics were numerous and vocal. Within the Royal Canadian Air Force, senior officers who had flown Sopwith Camels in the previous war dismissed wooden fighters as a regression to obsolete technology. In Parliament, opposition members questioned whether taxpayer money was being wasted on impractical experiments, while Canadian pilots flew British-built Hurricanes with proven combat records. Even within the engineering community, colleagues who respected de Havilland's abilities doubted whether wooden aircraft could meet the performance specifications demanded by modern air combat. The pressure was extraordinary and constant. Every technical problem became evidence of a flawed concept. Every production delay was cited as proof that Canadian industry lacked the sophistication for advanced aircraft development. And overhanging everything was the terrible arithmetic of war. Fighter command was losing pilots faster than training schools could replace them. The Luftwaffe was introducing improved variants of the Messerschmitt and Focke-Wulf fighters. Time was not neutral. Time favored the enemy. De Havilland descended the stairs to the factory floor, weaving between workstations where craftsmen shaped components with tools that would have been familiar to cabinet makers a century earlier. He stopped at the wing assembly area, watching a team carefully position the main spar, a laminated beam of Douglas fir that would carry the primary flight loads. The wood had been selected with obsessive care, each piece examined for grain orientation and defects, rejected if any flaw suggested weakness. It was beautiful in its way, the natural patterns of growth rings visible through the thin varnish coating, a reminder that this aircraft would be built from living things that had drawn sustenance from soil and rain and sunlight. A young woman working at the sanding station looked up as he approached. Her name was Margaret Chen, 23 years old, daughter of Chinese immigrants who had settled in Vancouver. Before the war, she had studied mathematics at the University of British Columbia, intending to become a teacher. Now she applied those mathematical skills to ensuring that curved wooden sections matched engineering specifications within tolerances tighter than most precision metalwork. She held a template against the wing section, checking the airfoil profile, then returned to her sandpaper with methodical patience. "Mr. de Havilland, may I ask a question?" Her voice was quiet but clear, cutting through the ambient noise of the factory floor. "Everyone says this aircraft cannot possibly work. They say wood is too weak, too unreliable, too primitive. But you keep building it anyway. What makes you so certain they are wrong?" It was the kind of direct question that people usually avoided asking in hierarchical settings, but Chen had a reputation for intellectual honesty that sometimes bordered on uncomfortable bluntness. De Havilland appreciated it. The factory floor was no place for polite evasions. "I am not certain they are wrong. I am certain we have no alternative. The aluminum shortage is real. The casualties are real. If wooden fighters have even a reasonable chance of success, we must attempt them. Certainty is a luxury we cannot afford." Chen absorbed this, her expression thoughtful. "So we are building an aircraft on hope and mathematics." "Yes, and on the skill of people like you, who understand that precision matters regardless of the material being shaped. A wooden wing must be exactly right, just as an aluminum wing must be exactly right. The aircraft does not know or care what it is made from. It only knows whether the forces acting upon it are in balance." She returned to her work, and de Havilland continued his inspection tour, stopping periodically to examine joints, to check adhesive application, to answer questions from workers who were learning an entirely new craft under impossible time pressure. The weight of responsibility was physical, a tension in his shoulders that never fully released. If this aircraft failed, these people would return to their previous lives, their brief excursion into aviation a footnote in their personal histories. But he would carry the failure forever, the knowledge that his confidence had outstripped his competence, that his ambition had wasted resources and time that could have been applied to conventional solutions. A commotion near the entrance drew his attention. Harold Bishop entered at speed, his normally measured demeanor replaced by visible excitement. He carried a wooden panel approximately 1 meter square, its surface covered with a thin metallic coating that glinted under the factory lights. "Jeffrey, you need to see this immediately." The radar testing results from the Chalk River facility. They moved to de Havilland's office, a converted storage room with blueprints covering every wall surface and a desk buried under technical manuals and correspondence. Bishop set the panel on the desk with the reverence usually reserved for something fragile or valuable. "We coated this laminated birch with a thin aluminum paint, trying to improve weather resistance. The radar reflection increased as expected. But then we tested an uncoated section treated only with our standard varnish. The results were extraordinary." He produced a graph showing radar cross-section measurements at various frequencies. The treated wood showed a signature barely 20% that of equivalent aluminum structures. At certain angles, the reflection was so weak that the experimental radar sets at Chalk River had difficulty maintaining a consistent track. Bishop tapped the graph, his finger trembling slightly. "Jeffrey, do you understand what this means? A fighter built from treated wood would be nearly invisible to German radar at ranges beyond 10 kilometers. The Freya stations that track bomber formations would struggle to detect individual wooden aircraft until they were practically overhead. This is not just a substitute for metal construction. This is a genuine tactical advantage." De Havilland studied the data, his mind racing through implications. The Germans relied heavily on radar-directed defenses. Their night fighter tactics depended on ground controllers vectoring aircraft toward bomber streams detected at long range. Their anti-aircraft batteries used Würzburg sets to calculate firing solutions for high-altitude targets. An aircraft that could slip through those detection networks would have survivability characteristics far beyond what armor or speed alone could provide. But there was a darker side to this discovery. If wooden fighters possessed stealth characteristics, they would be directed toward the most dangerous missions, the deep penetration raids where radar invisibility mattered most. The pilots flying these aircraft would face extraordinary risks, knowing that their survival depended on an untested property of an unconventional material. If the stealth advantage proved less effective than laboratory testing suggested, if German radar technology improved faster than anticipated, those pilots would die in aircraft made from trees, mocked even in death by skeptics who had opposed the program from the beginning. Have we verified this independently? Are we certain the results are not artifacts of the testing methodology? Bishop nodded, anticipating the question. The National Research Council team at the University of Toronto replicated the tests using different radar frequencies and measurement techniques. The results were consistent. Treated laminated wood exhibits significantly lower radar reflectivity than aluminum alloys across all militarily relevant frequencies. The physics are sound. Then we need to inform Air Marshal Edwards immediately. This changes everything. It transforms our proposal from a desperate improvisation into something with genuine strategic value. Bishop hesitated, his expression troubled. Jeffrey, I must ask you to consider the ethical implications. If we promote this aircraft primarily for its stealth characteristics, we are asking pilots to fly into heavily defended airspace in machines built from wood. If something goes wrong, if the structural integrity fails or the performance proves inadequate, those men will die in aircraft we convinced command to deploy. Are you prepared to carry that responsibility? The question cut deep because it was fair. De Havilland had been so focused on solving the technical problems, on proving that wooden aircraft could work, that he had not fully confronted the moral dimension of success. If this aircraft flew combat missions, if pilots died in it, their deaths would be partially his responsibility regardless of whether the design was sound. That was the burden of engineering in wartime. Every decision carried the weight of lives. Harold, pilots are dying right now in aluminum aircraft that radar tracks from the moment they cross the French coast. They are dying in machines we know are inadequate against current German defenses. If wooden fighters offer even a marginal improvement in survivability, we have an obligation to pursue them. The ethical failure would be allowing perfection to prevent progress. We do the best we can with what we have, and we accept that the best will sometimes not be enough. Bishop removed his glasses, cleaning them again, buying time to formulate his response. You are probably right, but Jeffrey promised me something. If the testing reveals problems we cannot solve, if the aircraft proves unsafe or inadequate, promise me you will have the courage to cancel the program regardless of political pressure or personal investment. Engineers must sometimes save people from their own inventions. I promise, and I will hold you to that promise because I am not certain I will have the strength to keep it alone. They returned to the factory floor, where the fuselage was being prepared for its skin. The process was mesmerizing in its complexity. Thin sheets of birch, each barely 2 millimeters thick, were coated with casein adhesive and layered over the frame in opposing grain orientations, creating a monocoque structure that derived its strength from the shell itself rather than from internal framework. Workers used vacuum bags to ensure uniform pressure during curing, a technique borrowed from composite boat building and adapted for aircraft production. McIntyre supervised the operation with intense concentration, checking adhesive consistency, monitoring temperature and humidity levels, ensuring that each layer was positioned exactly as the engineering drawings specified. One mistake here, one section that did not cure properly, or one area where adhesive penetration was inadequate, and the entire fuselage could fail catastrophically during flight testing. There were no second chances with monocoque construction. It worked perfectly, or it did not work at all. The afternoon shift changed over, workers exchanging places with practiced efficiency. De Havilland noticed increasing numbers of women on the factory floor, filling roles traditionally held by men who were now overseas or training for combat deployment. Margaret Chen was not unusual. Dozens of women operated lathes, assembled components, performed quality inspections with the same precision demanded of any worker. The war was transforming social structures as thoroughly as it transformed industry, creating opportunities that would have been unthinkable 3 years earlier. As evening approached, the factory lights came on, harsh and industrial, casting sharp shadows across the workspace. De Havilland found himself standing before the partially completed fuselage, studying the smooth curves of laminated wood, trying to imagine this static object transformed into something dynamic and purposeful. It looked fragile, almost delicate, despite the engineering that insisted otherwise. Could this really carry a pilot into combat? Could it withstand cannon fire, violent maneuvers, the brutal stresses of air combat? Robert McIntyre appeared beside him, his day's work evident in the sawdust coating his clothing and the fatigue lines around his eyes. She is beautiful, is she not? I've built racing yachts that won championships, furniture that sits in Parliament, but I have never built anything like this. Wood shaped not just for function, but for survival, for speed, for purposes I barely understand. It feels almost sacred, in a strange way. De Havilland understood. There was something profound about using living material, about transforming trees that had grown for decades or centuries into instruments of war. It felt both natural and transgressive, as if they were asking the forests themselves to join the fight against fascism. Tomorrow we begin the wing assembly, McIntyre continued, if your revised lamination schedule works. If the thinner layers cure properly, we might complete the first prototype by November. Then comes the moment of truth. Ground tests, taxi trials, and eventually flight. Are you ready for that moment, Mr. de Havilland? Ready to see whether your mathematics translate into an aircraft that actually flies? The question hung in the air between them, weighted with all the uncertainty and hope that defined this entire endeavor. De Havilland thought about the telegram that had started everything, about Air Marshal Edwards' reluctant approval, about the hundreds of workers who had committed their skills to this unprecedented project. He thought about pilots over the channel, about radar stations tracking them to their deaths, about the possibility that Canadian forests might offer salvation. I am as ready as I will ever be. But Robert, I want you to know something. If this aircraft fails, if my calculations were wrong or my confidence misplaced, the responsibility is mine alone. You and your team have executed the construction flawlessly. Whatever happens next is on me. McIntyre smiled, tired but genuine. Jeffrey, we are all in this together. When that aircraft flies, if it flies, the success belongs to everyone in this factory. And if it fails, well, we will carry that failure together as well. That is what it means to be Canadian. We do not abandon each other when things get difficult. They stood together in silence, two men from different worlds united by the belief that trees and mathematics and human ingenuity might somehow be enough. Around them, the factory continued its work, the sound of saws and sanders and careful conversation blending into the ambient music of creation. Outside, darkness fell across Ontario, and somewhere across the Atlantic, the war continued its grinding mathematics of destruction. But here, in this converted warehouse in Downsview, possibility remained alive. The first wooden fighter was beginning to exist, transitioning from theory into physical reality, and with it came the burden of hope that it might actually matter. December 1941, Malton Airfield, Ontario. Aero 615 hours. The first prototype sat on the frozen tarmac, its wooden skin pale against the gray pre-dawn sky. Frost coated the wings, delicate crystals forming patterns that emphasized every seam and joint in the laminated construction. To the assembled observers, military officers and engineers huddled against the December cold, the aircraft looked impossibly fragile, a child's toy scaled up to adult dimensions. But Jeffrey de Havilland saw something else. He saw 2 months of calculations validated, saw construction techniques proven, saw the possibility that desperation and ingenuity might produce something worthy. Test pilot Philip Murray completed his pre-flight inspection, moving around the aircraft with methodical attention. Murray was 34, a former bush pilot from Manitoba who had flown everything from crop dusters to float planes before joining the RCAF test program. He had the kind of instinctive feel for aircraft behavior that could not be taught, only developed through thousands of hours interpreting the subtle messages transmitted through stick and rudder. His expression revealed nothing. If he felt any anxiety about flying an aircraft built entirely from wood, he kept it buried beneath professional composure. De Havilland approached as Murray completed his inspection. The control surfaces are responding properly, no binding, no excessive play. The engine temperatures are nominal. She looks ready, Mr. de Havilland. The question is whether your mathematics are ready. It was a fair question. Wind tunnel testing predicted good aerodynamic performance. Static load tests confirmed structural integrity. But nothing fully replicated the complex interaction of forces during actual flight. An aircraft was not a collection of components. It was a system, and systems had emergent properties that sometimes surprised even their designers. The wooden fighter might fly beautifully. It might handle like a pig. It might come apart in mid-air. The only way to know was to try. Air Marshal Edwards stood apart from the main group, watching through binoculars focused on the prototype. He had approved funding for 3 aircraft, enough to conduct meaningful testing, but limited enough to minimize losses if the program failed. His support had been grudging, extracted only after de Havilland presented the radar stealth data and argued that tactical advantage justified technical risk. But Edwards was a practical man who measured success in operational effectiveness, not innovative design. This morning would begin determining whether Canadian engineering audacity translated into military capability. Murray climbed into the cockpit, settling into the seat with the efficient movements of someone who had done this hundreds of times before. The canopy closed with a solid thunk, surprisingly reassuring despite the wooden frame. De Havilland found himself holding his breath as the engine coughed to life, the Merlin power plant rumbling with mechanical confidence. At least that was metal, proven, reliable. The airframe might be experimental, but the engine was the same unit that powered Spitfires and Hurricanes across the European theater. The prototype taxied toward the runway, moving slowly across the frozen ground. Workers from the Downsview factory had driven out before dawn to witness this moment, their faces visible in the growing light, equal parts pride and anxiety. Margaret Chen stood near the front, her arms wrapped against the cold, watching the aircraft she had helped shape move toward its moment of truth. Murray ran up the engine at the runway threshold, checking magnetos and control response. Through the canopy, his silhouette was barely visible, just the outline of helmet and shoulders. Then the throttle advanced, and the wooden fighter began its takeoff roll. The acceleration was swift, quicker than de Havilland had calculated. The lightweight construction meant less mass to accelerate, and the engine power was more than adequate. The tail lifted, and suddenly the aircraft transitioned from ground vehicle to something else, something graceful. At precisely the moment de Havilland's mathematics predicted, the prototype lifted into the cold December air. It flew. The simple fact of flight seemed almost miraculous. Wings made from Sitka spruce carried the aircraft upward, the laminated monocoque fuselage held together, the control surfaces responded to pilot inputs. Murray executed a gentle climbing turn, gaining altitude while staying within gliding distance of the airfield. Every observer on the ground tracked the aircraft with silent intensity, waiting for the catastrophic structural failure that skeptics had confidently predicted. But the wooden fighter continued flying, climbing to 3,000 feet, then executing a series of gentle maneuvers. Shallow turns, pitch changes, coordination exercises. Murray was feeling out the aircraft, learning its personality, discovering how it responded to control inputs. His radio transmissions were clipped and professional. Control response is crisp, no unusual vibrations. Stability is excellent. I'm going to try some moderate aerobatics. De Havilland felt his stomach clench. Aerobatic maneuvering would stress the airframe in ways ground testing could not replicate. If the laminated construction had hidden weaknesses, aggressive flying would expose them. He watched through borrowed binoculars as the prototype climbed higher, then rolled inverted, hanging upside down for several seconds before rolling upright again. A loop followed, the aircraft tracing a perfect circle against the gray sky. Then a series of barrel rolls, the wooden fighter spinning along its longitudinal axis with mechanical precision. The airframe held, every maneuver completed without visible distress. Murray's voice came through again, and this time there was audible excitement breaking through his professional reserve. Gentlemen, this aircraft handles beautifully. The roll rate is exceptional, better than a Hurricane. The pitch authority is excellent, and the stall characteristics are remarkably gentle. Whatever concerns you had about wooden construction, they are not manifesting in flight performance. The test continued for 40 minutes, Murray pushing incrementally harder with each maneuver, building confidence in the aircraft's capabilities. He conducted high-speed dives. Pulling out with forces that stressed the wing spars to their design limits, he practiced simulated combat maneuvers, tight turns, and rapid altitude changes. He tested single-engine handling, shutting down the Merlin and restarting it at altitude. Every test revealed an aircraft that performed as designed or better. Finally, Murray brought the prototype in for landing, executing a textbook approach that put the wooden fighter precisely on the runway centerline. The touchdown was smooth, the rollout controlled. As the aircraft taxied back toward the assembly area, the workers erupted in spontaneous cheering, the kind of unguarded celebration that months of anxiety finally released. Murray climbed from the cockpit with deliberate slowness, removing his helmet and gloves before facing the assembled crowd. His expression was carefully neutral, but his eyes betrayed genuine enthusiasm. Air Marshal Edwards approached first, accompanied by several senior officers whose skepticism was evident in their body language. "Well, Flight Lieutenant Murray, does this wooden contraption actually work?" Murray chose his words carefully, aware that his assessment would influence decisions affecting the entire program. "Sir, it more than works. It is one of the finest aircraft I have flown. The handling characteristics are superb, the performance margins are generous, and the construction appears completely sound. If I were asked to take this aircraft into combat tomorrow, I would do so with absolute confidence." The statement landed with visible impact. Officers who had dismissed wooden fighters as desperate folly were forced to reconsider. The mathematical predictions had been validated by flight testing. The unorthodox construction had proven itself in the demanding environment of aerobatic maneuvering. What had seemed impossible 3 months earlier was now demonstrated fact. Sitting on the tarmac in the form of an aircraft built from trees. But Edwards was not finished. "The handling is one thing, Murray. Combat survivability is another. How do you think this aircraft would fare against cannon fire?" Murray's expression darkened. "Sir, I think it would fare poorly, just as aluminum aircraft fare poorly against cannon fire. But the wooden construction might offer advantages that metal cannot. Smaller radar signature, as the engineers predicted, and possibly better survivability against incendiary rounds, since wood tends to self-seal bullet holes rather than propagating tears like aluminum skin." De Havilland stepped forward, sensing an opportunity to expand on Murray's assessment. "Sir, if I may, we have conducted ballistics testing on laminated wood samples. The results are surprising. At certain angles, projectiles pass through cleanly without causing the catastrophic structural failure you see with metal. The wood absorbs energy differently. It splinters locally but does not transfer stress across the entire structure. I am not claiming wooden aircraft are invulnerable, but they may be more resilient than conventional wisdom suggests." Edwards studied the prototype with renewed interest. The aircraft stood quietly on the tarmac, frost melting from its wings in the growing daylight, looking ordinary and extraordinary simultaneously. "Very well, I am authorizing expanded production. 20 aircraft initially, with provisions for larger orders pending combat evaluation. But Mr. de Havilland, understand this clearly. If Canadian pilots die because wooden construction proves inadequate, that responsibility will be yours." The words hung in the cold air, a reminder that success in flight testing was only the beginning. The real test would come over occupied Europe, where radar stations tracked hostile aircraft and German fighters prowled with lethal efficiency. The wooden fighter would prove itself or fail in an environment where mistakes meant death and second chances did not exist. January 1942, Royal Canadian Air Force Station, Northolt, England. 2,140 hours. 4 wooden fighters sat in the dispersal area, their non-reflective finish making them nearly invisible against the dark tarmac. The aircraft had been shipped to Britain in late December, crated and stowed aboard a fast convoy that evaded U-boat patrols through a combination of routing luck and escort carrier protection. 3 weeks after leaving Halifax, the fighters were reassembled at Northolt on the western outskirts of London and assigned to a special detachment conducting night intruder operations against German airfields in occupied France. Squadron leader James Mackenzie briefed his pilots in a Quonset hut warmed by a single coal stove. Mackenzie was 28, a veteran of the Battle of Britain who had transitioned from day fighting to night operations when injuries from a bailout left him with reduced visual acuity. He studied the wooden fighters with open curiosity mixed with professional skepticism. "Gentlemen, Command has assigned us these Canadian-built aircraft for evaluation under combat conditions. They are constructed primarily from wood. They allegedly possess reduced radar signature, and they are completely untested in actual operations. We are going to change that tonight. The target was a Luftwaffe night fighter base near Rouen, approximately 80 kilometers inland from the French coast. Intelligence indicated the field housed Ju-88 night fighters that had been intercepting RAF bomber streams with increasing effectiveness. The mission was straightforward. Penetrate to the target under cover of darkness, strafe aircraft and facilities, egress before German defenses could respond. Success depended on stealth and speed. The wooden fighter's low radar profile would be tested against Freya early warning stations along the coast. Mackenzie climbed into his aircraft, settling into the cockpit that still smelled faintly of varnish and wood. The instrument panel was conventional, the controls familiar, despite the unconventional construction. He ran through the pre-flight checklist, noting the solid feel of everything, the quality of construction that suggested Canadian workers had taken this seriously. The engine started smoothly, and within minutes, 4 wooden fighters were taxiing toward the runway, disappearing into the darkness like ghosts reluctantly returning to haunt familiar territory. They flew low across the channel, barely 50 feet above the waves, using the sea return to mask their radar signatures from German coastal stations. The wooden construction helped, but tactics mattered more. Radar could not track what it could not distinguish from background clutter. Mackenzie monitored his compass and airspeed, navigating by dead reckoning across black water toward a hostile coast. The French shoreline appeared as a darker line against dark sky. The formation climbed slightly, crossing the beach at 200 feet, then immediately dropped back to treetop level. No searchlights stabbed upward. No anti-aircraft fire erupted. The Freya stations that normally detected incoming raiders at 50 kilometers remained silent. Whether this was due to the wooden construction, the low altitude, or simply German inattention was impossible to determine. But they were across the coast, penetrating inland, and no one was shooting at them yet. The landscape below was invisible except for occasional lights marking towns under blackout discipline. Mackenzie flew by instruments and instinct, trusting his navigation and hoping the target coordinates were accurate. Navigation errors on night intruder missions meant returning home with bombs or ammunition unused, explaining to superiors why you had failed to find a stationary target in occupied territory, but the airfield appeared exactly where intelligence had placed it, outlined by subtle perimeter lighting meant to guide returning German aircraft. Mackenzie could see the dark shapes of aircraft dispersed around the field, possibly 6 or 8 Ju-88s sitting exposed. He armed his guns, rolled into an attack dive, and opened fire. The wooden fighter shuddered as its cannons fired, tracers arcing downward to impact against a parked aircraft. Fuel ignited, flames erupting with immediate violence, illuminating the airfield in flickering orange light. Mackenzie pulled up hard, banking away as anti-aircraft batteries opened fire, their shells detonating where he had been seconds earlier. Behind him, the other wooden fighters made their passes, adding to the destruction, their guns ripping into aircraft and buildings before climbing away into protective darkness. The egress was chaos. Searchlights probed the sky, anti-aircraft fire filled the air with steel fragments, and somewhere a German night fighter was scrambling to intercept. Mackenzie dove for the deck, pushing the wooden fighter to its speed limits, racing westward toward the coast. Behind him, Rouen burned. The mission was successful, but survival depended on reaching the channel before German defenses organized an effective response. The coast appeared suddenly, and Mackenzie was across it, dropping to wavetop height, allowing the sea return to swallow his radar signature once again. No German fighters followed. Either they had not detected the raiders, or the wooden construction had prevented effective radar tracking, or luck had simply favored the Canadians tonight. Regardless, 4 wooden fighters returned to Northolt intact, their first combat mission completed successfully. Mackenzie shut down his engine in the dispersal area, suddenly aware of fatigue and adrenaline crash. The wooden fighter sat quietly, its structure undamaged despite the violence it had just participated in. He walked around it slowly, running his hand along the smooth wooden skin, trying to reconcile the fragility it suggested with the performance it delivered. A ground crew sergeant approached, clipboard in hand, ready to document any damage or maintenance requirements. "How did she perform, sir?" Mackenzie considered the question carefully, thinking about the low radar signature that had allowed penetration of German defenses, the handling characteristics that had facilitated precise attacks, the structural integrity that had survived combat without complaint. She performed perfectly. "Sergeant, whatever skepticism I had about wooden construction is gone. This aircraft is the real thing." March 1942, de Havilland Facility, Downsview, 15:30 hours. Geoffrey de Havilland read the combat reports from England with a mixture of vindication and humility. 23 operational missions without structural failure, multiple confirmed kills against German aircraft. No losses attributable to construction deficiencies. The wooden fighter had proven itself under conditions that mattered, validating the mathematics and the manufacturing techniques and the audacious belief that trees could fight wars. Production had expanded dramatically. The initial order for 20 aircraft had grown to 200, with additional contracts under negotiation. Factories across Ontario were converting to wooden aircraft production, training workers in lamination techniques and quality control procedures. The aluminum shortage that had sparked the entire program remained acute, but now Canada had an alternative, a way to contribute fighter aircraft without competing for scarce metal resources. Harold Bishop entered the office carrying a technical journal, his expression thoughtful. "Geoffrey, there is an article here from the Massachusetts Institute of Technology about radar-absorbent materials. They are researching synthetic compounds that could reduce radar signatures even further. The implications for our wooden fighters are significant. If we could coat the airframe with radar-absorbent paint, we might achieve near invisibility to current German radar systems." De Havilland accepted the journal, scanning the article quickly. The research was theoretical, years away from practical application, but it represented the next step, the evolution of stealth technology from accidental discovery to deliberate engineering. The wooden fighter had begun as a desperate response to material shortage. It was becoming something more significant, a demonstration that unconventional thinking could produce genuine tactical advantages. Margaret Chen appeared in the doorway holding a wooden sample that showed experimental finishing techniques. "Mr. de Havilland, I have been working with the chemistry department at the University of Toronto on improved varnish formulations. This one incorporates carbon particles that should further reduce radar reflectivity while maintaining weather resistance. Would you like me to prepare samples for testing at Chalk River?" He would. The program was no longer just about building aircraft. It was about continuously improving them, refining techniques, pursuing marginal advantages that might save pilots' lives. That was engineering at its best, the relentless optimization driven by knowledge that human survival depended on getting details right. Through the office window, he could see the factory floor where additional wooden fighters were taking shape. The construction that had seemed so strange 4 months earlier now appeared normal, even elegant. Workers moved with practiced efficiency, their skills honed through repetition and mistakes and incremental improvements. Canada had developed an indigenous aircraft industry based on its natural resources and its people's adaptability. The wooden fighters were not copies of British or American designs. They were distinctly Canadian, born from necessity and perfected through determination. Robert McIntyre joined them, his presence filling the small office. "Geoffrey, I wanted you to know something. My son enlisted last week. He is training as a pilot. There is a reasonable chance he will fly one of these wooden fighters we have built. That thought terrifies me and makes me proud simultaneously. We have created something that might keep him alive. That is more meaningful than any engineering achievement." De Havilland understood completely. The abstraction of aircraft design had become intensely personal. These were not just machines. They were life support systems for young men flying into lethal environments. Every design decision, every manufacturing shortcut avoided, every quality control procedure enforced, all of it mattered because human lives depended on getting it right. The war would continue for years yet, its outcome still uncertain despite Allied confidence. More wooden fighters would be built, flown, lost. Some pilots would survive because of the stealth characteristics that radar could not track. Others would die regardless because combat was unforgiving and even the best aircraft could not guarantee survival. But Canada had contributed something genuine, something that emerged from its forests and factories and the ingenuity of people who refused to accept that conventional limitations applied to them. Geoffrey de Havilland stood at the window, watching workers shape wood into weapons, watching mathematics become reality, watching hope take physical form. The wooden fighter had proven that aluminum was not the only path forward, that unconventional solutions could succeed when pursued with sufficient rigor and courage. It had proven that Canadian engineering could innovate rather than merely imitate. Most importantly, it had proven that trees, properly understood and carefully shaped, could help win a war against an enemy that believed only steel and ruthlessness mattered. Outside, snow began falling across Ontario, covering the factory and airfield in white silence. Inside, the work continued, the transformation of living wood into instruments of survival, the quiet Canadian contribution to a global struggle for survival and sanity. The wooden fighters would fly through European skies, invisible to radar, resistant to conventional expectation, a testament to what was possible when necessity and ingenuity converged. They were not perfect. They were simply good enough, deployed when they were needed most, and that made all the difference.